Welcome to lecture number 5 of our system protection course. So we'll talk about, in this lecture also we'll talk about the CTs and PTs. So in the last class we discussed about the CTs, about the performance of CTs, the equivalent circuit model, and also we have seen different types of IEEE standard models, T class and C class CTs, and how they are being in use. So in this class we'll see when in fact, because CT and PT, they're the transformers, and in fact when there is a DC offset current because of the uh, switching phenomena in the transmission line. So because of that, the core of the CT and PT, it saturates very quickly. So therefore, it is very important that before the CT gets saturated, the relay should operate. And if it is not, then the relay will maloperate. So let us see in this class how the DC offset current is being produced, what is the nature of the DC offset current, and how it will saturate the CT core, and ultimately how it affects the performance of CT. Let us see it. So CT saturation and DC offset current. Typically, fault current consists of a symmetrical AC component, and also it consists of symmetrical AC components and also a DC offset current. How the DC offset current produced? It is because of the inductive nature of the transmission line or various loads connected to the circuit. To understand this issue, let us consider an unloaded transmission line. Okay, let us consider an unloaded transmission line which is excited by a voltage source. Okay, so let us consider a transmission line with a R line as resistance and L line as the inductance of the line. Then the voltage source is connected here. It is Vm sine omega t plus phi. Phi is the phase angle of the voltage with respect to the reference. Now the switch is being closed. That means it will just simulate the fault, right? It will simulate the fault here. At t equal to 0, if we'll close the switch, that means it is short circuited. That will just simulate the fault. Okay, so let us assume that IT equal to 0 for this from 0 to t naught, and at t naught the switch is being closed, and as we know this is a RL circuit. So for RL circuit already we have seen these equations, or we have already derived this equation, and this is a basic electrical engineering subject matter. So if we'll derive IT, we'll find Vm by Z line sine of omega t plus phi minus theta, where phi is the phase angle of the voltage and theta is the angle of the impedance of the transmission line, plus I0 e to the power minus t naught by tau, because t naught is the time at which the switch is being closed to simulate the short circuit fault. And tau is the time constant, and tau is equal to L by R. Already we know this. And this equation is valid for t greater than equal to t naught. So if we'll derive I naught, how we can derive I naught? By just substituting the initial value, that IT0 just substituting IT0 is equal to 0, we can just derive I naught. Okay, so I naught will be nothing but is equal to minus Vm by z line sine of uh, omega t0 plus phi minus theta, right? Just by considering this initial condition, we can find I naught from the above equation. Okay. Now your IT will become Bm by z line sine of omega t plus phi minus theta. Then after substituting I naught, it will become minus of Vm by z line sine omega t naught plus phi minus theta e to the power minus t naught by tau. And if we'll plot this fault current or this short circuit current IT with respect to time, then how it will look like? It will be looking like this. You can see here, this is the plot of fault current versus time. Now your transient part will gradually, your DC offset will gradually become 0 as time passes. So your sinusoidal component gradually becomes steady. It will gradually become steady uh, after maybe 5 times of the time constant or 10 times of the time. Generally here we took 5 times of the time constant. So let us see how this is your the DC offset current we have seen already. This is your DC offset current, right? This is your DC offset current. And really, is it really affecting the saturation of the core? Let us see then. CT saturation due to DC offset current. Let us consider an ideal CT that is excited. We'll consider first an ideal CT excited by only by the DC offset current, not by AC, because we have seen the fault current is the sum of the AC component. One symmetrical AC component is there, and also the DC offset current is there. But here we'll only consider the DC offset current. Let us see what is happening to the flux. Okay, so now let us say the DC offset current is this one. Okay, this is your DC offset current, and it is being fed to the ideal CT. So CT is having N1 by N2 turns ratio, and the switch is being closed here at this point. Okay, at t equal to 0, and now your T to I2 will flow, okay, through R. R is the burden. Okay, now an ideal CT will faithfully uh, replicate the primary current waveform on the secondary side, right? So whatever primary current will flow through this, okay, so this is, let us say, I1T, okay, so whatever I1 will flow and it will faithfully replicate in I2. Though we are telling this a DC offset current, but it will replicate because the current is changing, right, with respect to time. So therefore a flux will be produced, and similarly replicate current. A current will replicate in the secondary side. Hence the secondary current would be given by, how it will be given by, just by multiplying the turns ratio. We'll get N1 by N2 I naught e to the power minus t by tau. Then what will be the voltage developed across CT secondary? That will be the current flowing in the secondary side, I2 into N2. I2 into R. R is your burden. Already we have seen here. Here is your R. Okay. R is here. This is your burden. Okay. So by multiplying with R, we'll get the uh, V2 DC, right? That means the voltage that will be across the secondary side will be N1 by N2 R times IO e to the power minus T by tau. Okay, so this will be your voltage developed across CT secondary. Okay, so if we'll plot this voltage, it will look like this. It will be similar to the current waveform. Okay, and now we know that V2 equal to N2 into d phi by dt, and now from this equation we can find the flux linkage or phi, right? Okay, so we can find phi will be just by integrating V2 with respect to time and putting the initial conditions. We'll find phi t equal to phi naught. So initial condition is at t equal to 0, phi t equal to phi naught. So this is your initial condition. So by substituting this initial condition, we'll find this equation, final equation, that is phi t will be equal to phi naught plus n1 by n2 square r of io, then tau 1 minus e to the power minus t by tau. So this is your flux linkage equation, and this is the flux which is in fact flowing through the core of the CT. Okay, now if we'll plot the flux, how it will look like? It will look like this. Okay, so if we'll plot the flux, it will in fact look like this. Okay, so this is your flux equation with respect to time. And we know the maximum value of IO is Vm by Z line. This is already we know, right? And it is the initial current, and it implies that phi DC max, so phi DC max can be as high as this. Okay, so therefore your phi DC max, that is here N1R by N2 square Vm by Z line, by substituting IO in your flux equation, we'll get the phi DC max. That means your phi DC max will become as high as this. Okay, now this phi DC max will be added to the AC flux which is linking the flux along with the core, right? So now we have inside the core we have two flux. One is your, because of the AC component, symmetrical AC component, and other component is because of the DC offset current. Will find this flux. Okay, so the voltage developed across the CT secondary by the steady state, that is sinusoidal component of the fault current, is given by, that is V2AC. will be similarly we can find this just by considering one symmetrical AC current across the primary. We'll find similar expression for V2AC, and from V2AC we can similarly find, by integrating we'll find the AC flux that is flowing in the core, right? Just by integrating V2AC we'll find phi AC. Now phi AC will be your RVM by omega by Z line N1 by N2 square and sine of omega t plus phi minus theta minus pi by 2. So in the similar fashion as we obtained the DC offset, as we obtained the DC flux because of the DC offset current, similarly we can find the AC flux as well by considering the AC current, then the voltage across the secondary side, then the flux. Okay, now your phi AC maximum, that is the maximum AC flux, will have RVM by omega z line N1 by N2 square. So this is your maximum AC flux. That means when we have a sinusoidal current applied, or we can say when there is a fault, we'll have two types of current in the current source or in the primary side current of the CT, and it is consisting of two components. One is, so your fault current is having, one is AC component, one is your AC component, okay, and other one is your DC component because of the DC offset, and both will lead to two flux, right? One is your phi AC plus phi DC, right? Now for this both of these flux will have two maximum components. One is phi AC max, other one is phi DC max. Okay. So now this will give us the phi max. That is the maximum phi, and in fact this will lead to the core saturation. Okay. Because if the DC component or DC offset is not there, then this component would have been 0. Okay, so because of the DC offset, this component is coming into picture, and it will lead to more maximum flux, and by that way it will again lead to the saturation of the core. Okay, so now we can see the phi total maximum flux, already I told, that will become this. Okay, this will be phi AC max plus phi DC max, that is equal to RVM by omega z line N1 by N2 square, and also plus N1 by N2 square RVM tau by z line, right? So this is your maximum we can say maximum flux that can be produced in the core of the city. Now if we look like the flux, if we'll plot it with respect to time, it will in fact a sinusoidal component, but in fact it will increase like this, right? And it will saturate. Okay. So gradually it will saturate to a constant value. So that is the flux. Okay. So because of the saturation, CT secondary current clips. Because of the saturation of the core, because as the maximum flux value is increasing because of the DC offset current, so therefore the CT core will saturate very quickly, and because of the saturation, the secondary current in fact in the CT side will clip. It will look like this. Already you have studied this in the transformer course, right? So it will in fact look like this, clipping current, and because of this, the RMS value of the current will reduce, and therefore the relay will become blind to the clipped current. So DC flux accumulates gradually. So already as I told, the DC flux will gradually accumulate, which depends on the transmission line time constant, right? So the DC flux will increase gradually. Already we have seen in the last figure, right here. It will gradually increase, right? It will gradually increase. So therefore, it will take time to So discipline accumulates gradually, which depends on it depends upon the time constant of the transmission line. So therefore, the saturation doesn't occur immediately after the fault. So it takes little time for to become saturation. So if the relay is fast enough, then the relaying decision would be taken easily. So this is another reason why, in fact, we need the speed in the relay operation, faster relay operation, because if it is faster, then the decision will be taken faster and it will be very accurate, right? Even sometime when the time delay is there, so it is sometime the relay gets saturated and the maloperation happens. So we'll discuss more about this. Now we can see here, this is why the saturation happens. It is because of this, right? Because of this BH curve. We know this already you have studied in your Mason's course as well, right? So when we apply sinusoidal voltage, the BH curve in fact looks like this, right? Okay, and it starts from here, and it gradually goes up, then it reverses, then again it goes up, right? The cycle follows as the AC. But when the AC component is mixed with the DC component, then obviously this knee point will be lesser as compared to the only AC component, right? Okay. So because of this, we in fact, in order to avoid the saturation of the core, we need the core cross section, or the cross section of the core, to be large. If the core cross section will increase, the core cross section will become larger, then the saturation will take time, and sometimes it is avoided, right? So therefore, we'll now analyze how much we can enlarge the core of the city. Is it possible, in fact, to enlarge the core of the city which is being used in the distribution and transmission line? Let us see. So we define this oversizing factor of the core, as core oversizing factor, as 1 plus phi dc by phi ac, or we can write this as phi max by phi ac max, because phi ac max is your original maximum flux. This is original maximum flux, right? And this is in fact the sum total of the phi AC max plus phi DC max. So phi DC max is because of the DC offset current. And now substituting this, we'll get 1 plus phi DC max by phi AC max. And just by substituting the phi DC max expression and phi AC max of expression, we'll find 1 plus omega tau. And just by substituting tau, we'll find 1 plus omega L line and R line. L line is your inductance of the total line length, or total line, inductance of line. Right, so this is your resistance of the line. Resistance of line. Right, this is for total line length. Now if we'll divide it in order to get so if we'll express it in reactance form, it will become 1 plus X line by R line, right? Okay. So this gives us, in fact, the oversizing factor. And we know that for a distribution line, your L by R ratio is approximately, it is 10 times. Sorry, not distribution line. Distribution line, in fact, it is very less. Sorry. It is for the 220 kV transmission line. it is approximately 10. So if we'll substitute this kV transmission line. So now if we'll substitute this value here, it will become around 11, right? So that means we have to increase the cross section of the core 11 times. We have to increase the core cross section 11 times for a 220 kV line, and it is in fact really difficult in practice to consider a very huge bulky CT, right? Similarly, for 400 kV transmission line, 400 kV transmission line, your L by R ratio is around approximately equal to 20, and if we'll see it, we have to increase the cross section. We have to increase the cross section around 21 times. So it is, if we'll do this in practice, in fact your CT will become very bulky and very heavy, and also it is very big size and the cost will increase. So very difficult to accommodate this kind of oversizing factor in order to avoid the saturation because of the DC offset current. So therefore it is generally avoided to consider this oversizing factor in design, and therefore your CT will be designed based on your AC flux or the AC flux requirement or the symmetrical fault current because of the AC component only, and then the operator has to take very faster or the relay should be designed in such a way that it should take the faster decision, so that in order to avoid the effect of saturation on relay decision. Okay, so this is your CT oversizing factor. Okay, so now let us see cautions in the CT selection. So what are the cautions we take in CT selection? While choosing a CT for a particular application, it is necessary to observe the following precautions. The CT rating and the continuous load current. So we should mark here, CT rating and the continuous load current should match. Unless that, we should not use that CT. For example, if maximum load current is 90 ampere, let us say, and a CT of 100:5 ratio may be acceptable, but 50/5 is not acceptable because the continuous load current or the maximum load current is 90 ampere, so 50/5 is not acceptable. The maximum fault current should be less than 20 times the CT rated current. Okay, for example, 100:5 CT can be used so long as burden and the CT is within the rated values. That is, the maximum primary fault current is below 2000 ampere, then only we can use 100:5 CT ratio, right? The voltage rating of the CT should be compatible. For example, 100:5 C100 would be linear response up to 20 times the rated current, up to the 20 times of the rated current. So then it is provided the CT burden is kept below 1 ohm, right? If we'll calculate the CT burden, already you have seen this type of example. If we'll calculate the CT burden for a C100 CT with a CT ratio of 100:5, then the burden will come 1 ohm, and with 2 ohm in fact as burden, this CT can be used only if the maximum current is limited to 1000 ampere. So when your burden is 1 ohm, we can use this CT up to 2000 ampere fault current, but when the burden increased to 2 ohm, it cannot be used for 2000 ampere fault current. Up to 2000 ampere fault current, it can be used for 1000 ampere fault current. Okay. This is very simple calculation, you can see it. So now let us see the voltage transformer or the potential transformer. So up to this we have discussed the uh, current transformer analysis and current transformer only, and also we have seen the uh, phase angle error and the how to calculate the ratio error, phase angle error for the CT. Now let us do the analysis for voltage transformer. So let us first see the equivalent circuit model of the voltage transformer. So unlike the current transformer, the voltage transformer, in fact, it is very much similar to the transformer used in the transmission network or the distribution network, which are used for step up or step down the voltage, step down the voltage. So now let us see the equivalent circuit. Already you have seen the equivalent circuit of a transformer in your machines course, right? I should not tell much about this. A voltage source is connected here in the equivalent circuit. Here R1 and X1 are the primary side resistance and the reactances. X1 is the leakage reactance, and N1 N2 they are the turns ratio. Okay, and R2 is the resistance of the secondary side, X2 is the leakage reactance of the secondary side. And also we have burden here. Burden is nothing but relay. So the equivalent circuit here is exactly like equal to the transformer, right? So now the question is, we are generally converting here because the standard voltage, secondary side voltage of the standard secondary voltage of Vt is 110 volt, and when we are using this Vt, we are measuring the transmission line voltage up to 400 kV, 765 kV, 220 kV, right? So then in that case, if we'll see the turns ratio, or if we'll see the ratio, voltage ratio or turns ratio, it is very huge, right? And as it becomes huge, the turns ratio, the transformer design itself, it becomes very bulky, and the size becomes very huge, and the cost also increases because of the more number of turns we use, more number of copper is required. So therefore, the transformer becomes very costly and bulky. So in order to avoid that, we use the capacitances to divide the voltages, and finally the small voltage is applied across the Vt, the primary of the Vt, right? Now you can see in this figure, right? In this figure what we are seeing here, we have two capacitance is connected as potential divider, and then the voltage is applied, voltage across C2 is applied across the Vt. Here it is shown an ideal CT, right? Sorry, ideal Vt across the Vt. In fact, it is the voltage transformer, right? So this is the ideal Vt, right? And ZB is the burden. Now, if we'll draw the equivalent circuit for this, how it will look like? Let us see. The equivalent circuit for that capacitances which are used as potential divider. And the ideal VT, if we'll make the equivalent circuit, because in case of ideal transformer there is no resistance, no leakage reactance we are neglecting, and here we are just transferring the ZB to the primary side, that will become A square ZB, and your Thevenin equivalent reactance will become 1 by j omega 1 by j omega C2 plus C1, and here your Thevenin voltage will be here VTH, right? Thevenin voltage is nothing but the voltage across the C2, capacitance C2. Okay, so now this circuit becomes simplified. Now the question is, whatever voltage will take across C2 will not be in fact fed to the relay, right? Because of the drop here, because of the drop at the capacitance, right? So in order to avoid this, we need to put a reactor, which we call the tuning reactor, which in fact compensates the effect of the capacitance, right? And in order to nullify that, we'll put a reactor that is called tuning reactor. So now we can see this here. This is your tuning reactor, right? Tuning reactor, which in fact compensates the effect of the capacitance, right? Okay, and therefore after compensating the capacitance using the tuning reactor, then we can see that this VTH, the Thevenin voltage, that is the voltage across C2, will be directly fed to the burden, right? Okay, so therefore we need the tuning reactor. Also, tuning reactor has added advantage, we'll see it in the future classes. Now we can see how the tuning reactances or tuning reactor is helping in fact compensating, right? We can see here. Now this is your equivalent circuit with the tuning reactor, and the voltage drop across the capacitance is Vc, and the voltage drop across the reactor is VL, which must be equal in order to feed the VTH directly without any distortion to ZV, right? Okay. So now we'll stop here. I will continue in the next class, lecture number 6. Thank you very much for your kind attention.